All right, let's take a look through this practice test here. All right, so on these problems, we're finding absolute max and absolute min. So we're not asked to find locals. I don't have to do like first derivative, second derivative test, any of that. I'm just going to find the critical values, check all the critical values, and check the endpoints. So here, let's take the derivative. We're going to get 3x squared minus 3. Set that equal to 0. I could pull a 3 out there. That's x squared minus 1. And like you should just be able to see, that's x minus 1, x plus 1. So my critical values are 1 and negative 1. So I need to check in the original, both endpoints, both critical values, and we'll see who's the biggest and who's the smallest. F of 0, that's just going to be 1. You can check all these on your own. F of 1 is going to be 1. That's 2 minus 3, negative 1. F of negative 1, I should have done these in order. In fact, here, let me go up here and put negative 1 on top. Let's see, that's going to be negative 1 plus 3 plus 1. With that 1 and negative 1 will cancel out. I think we get 3. Definitely check my arithmetic here. And then F of 3 is going to be 27 minus 9 plus 1 to be 18, 19, I think. Okay, so there's my global or absolute min. And there's my global or absolute max. So we'll circle those. Okay, here it's the same game. Let's find our critical values by taking the derivative. Derivative natural log of anything is 1 over that thing times the derivative of what's inside. So let's see, the derivative there is going to be 4 minus 2x. I want to figure out where this thing either equals 0 or does not exist. A couple places it does not exist because we have domain issues in the bottom here. I'm going to write this as 4 minus 2x. Let me write that a little better. I don't know if that's better. Over x times 4 minus x. Okay, so let's see the top. So G prime equals 0. When the top equals 0, that's at x equals 2. Does not exist. That's when the bottom equals 0 at 0 and 4. 0 is not even in my interval, so I don't care about that one. I do care about this one. So I need to check all of these values in the original if they exist. Like this one here, the original won't even exist there. That's oh, he's not in my interval. Don't care. Never mind. Don't even care. I only care between 1 and 3. I think we have a vertical asymptote there at 4 anyways, and at 0. So like that would not be, this function's not defined at 0 or 4, the original. So the extreme value theorem wouldn't have even applied. So we don't have to worry about that. All right, so now we got to check this critical value and these endpoints. So let's see, G of 1 be natural log of 4 minus 1. That's natural log of 3. G of 2 will be natural log of 8 minus 4. That's ln of 4. It's a 2 minus 4. Yep. G of 3 would be natural log of 12 minus 9. That's also ln of 3. Okay, so there's my global max. And I have 2 global mins. Right here also. I have 2 different places where I have a global min. You can have more than one. All right, let's look at this guy. Now we should kind of be thinking ahead. This is a cubic, right? So we know our graph's going to go something like, something like that. So -8 and 2, we're going to be looking at some kind of range like this. My guess is, this is just purely speculation, that my minimum is going to occur here, and then I'm going to get some maximum at a point like that. That's what I'm guessing is going to happen. I don't know. Let's check and see. Too far. All right, let's take the derivative. What do we get? 24x squared minus, oh, we're getting some big numbers here. What is that? 162x minus 42. And we want to know where that equals 0. All right, well, we can definitely pull out an 8 out of everybody, I think. No. We're going to have to do some crazy factoring here. We can definitely pull 4 out of everybody. No, just a 2. That would be 12x squared minus 81x minus 21 equals 0. All right, I'm not going to watch you or make you watch me try to factor this. I'm going to do that using gets and check, and then come back when I have the right factoring. Okay, I could pull a 6 out instead of a 2, make numbers a little smaller, and this was supposed to be a plus right there. That should be a plus, not a minus. So this should be easier to factor now. I think we get 4x and x, and I think we're going to get here a +7 and a -1. That would be, does that do it? Yeah, that would be 28x minus 1x is 27x. All right, we got it. Now we set each factor equal to 0. Of course, 6 never equals 0. And we're going to get x equals 1/4. And x equals -7. All right, so now we have to check in the original each one of these values. We're going to check -8, 1/4, 2, and -7. Oh, I should have gone in order here. Of 2. Okay, and I'm just going to do these off screen. You don't have to watch me type all those into the calculator. Okay, lost it. All right. Okay, here are the numbers I got. There's my max right there. And here's my min. So my original graph, I was wrong. I really thought the lowest point would be here. Okay, moving on. Now here we're just looking for concavity and points of inflection. So we only care about the second derivative here. Of course, we got to take the first derivative to get the second derivative, but we're not going to be doing increasing and decreasing, first derivative, sign chart, all that. So let's write this guy as x to the -3rd power. Then his first derivative will be -3x to the -4. And then his second derivative will be 12x to the -5, or 12 over x to the 5th. Okay, now let's do a sign chart for him. So any place where he equals 0, never equals 0. So f prime, double prime equals 0. Nope, never happens. What about does not exist? Yeah, at x equals 0. So that's not going to be a point of inflection, because it's the original isn't even defined at 0. We're not going to have a point of inflection. We are going to change concavity there, but points of inflection are points on the graph, and there is no point at 0. All right, if we could see pretty quickly, you plug in any negative value here, say plug in -1, -1 to the 5th power is a negative. We're going to get a negative. That means we're concave down. And you plug in any positive number, say 1, you're going to get a positive, so concave up into this. This is what we're plugging into. So this function is concave down on the interval -infinity to 0, always parentheses on all of our increasing, decreasing, and concavity. And then we're concave up from 0 to infinity. Okay, this guy looks like he'll be more interesting. So let's take his first derivative. What do we get? 6x squared minus 24. Let's take his second derivative. We get 12x. Okay, where are our possible points of inflection? Where g prime equals 0. You can see pretty quickly that's when x equals 0. Does not exist, that guy always exists. We don't have to worry about that. So we do a sign chart here for the second derivative. Let me write this. This is a sign chart for g double prime. So I'm plugging values in here. Again, plug in -1. You get -12, you get a negative. Plug in a +1. You get 12, you get a positive. So that's concave down and up. Now, that is a point on the graph. The original function is defined at 0. So g of 0 will be, you can just plug it in, 2. That means the point 0.02 is a point of inflection or an inflection point because we're switching concavity there. We're concave down, -infinity to 0, and concave up, 0 to infinity. It's an ugly figure. All right, what's next? Oh, we got another one. All right, let's take his derivative. So x prime, or the derivative of x with respect to t, will be 12t cubed minus 24t squared minus 36t. And his second derivative, what is that? 36t squared minus 48t minus 36. Okay, we're going to have 2 possible points of inflection. And my guess is they'll both be points of inflection, but let's check and see. What can we factor out here? 12, I think. That'd be 3t squared minus 4t minus 3. And now we're going to have to figure out how to factor this guy. Let me check my arithmetic real quick. No, I'm not sure that's going to factor. I need to make sure that's going to factor before I spend 10 minutes on it. Okay, yeah, it's not going to factor, so let's use quadratic formula. So we want to set 3t squared minus 4t minus 3 equal to 0. So we'll get t equals opposite of b plus or minus square root of b squared minus 4 times a times c all over twice a. You should know quadratic formula. So that's 4 plus or minus, what do we got? 16 plus 48. 58, 64. That'd be 12 times 3. So 16 plus 36. Just type it in. 52. All over 6. Now, I'm going to go ahead and simplify that, because that's 4 times 13. And then square root of 4, of course, is 2. So that'd be 4 plus or minus 2 root 13 over 6. And I'm going to split this up as 4 6 plus or minus 2 root 13 over 6. So 2/3 plus or minus root 13 over 3. All right, so we've got 2 possible points of inflection. We've got 2/3 minus root 13 over 3 and 2/3 plus root 13 over 3. And I want to check the sign of this guy, plus or minus, in each of these regions. Okay, so root 13, that's smaller than 4. So let's just call that like 4/3. 2/3 minus 4/3 would be negative 2/3. I'm just looking for anything over here. So I could be like -5 is definitely smaller than that. And plug that in here and see what we get. So we're going to get 25, 75 plus 20 minus 3. I don't care. It's a positive. So we're concave up. And then anything in this region, maybe 0. So I can just quickly look and say, oh, that's going to be -3. That's a negative. We're concave down in this region. And anything over here, again, I could pick any number. I could pick 100, something that I can obviously see just by glancing at it, because I'm too lazy to type all that in the calculator. Like, here, let's do 100. 100 squared is big. It's much bigger than -40. Okay, it's going to be positive. Positive. Concave up. All of these points are in my domain, so they are allowed to be points of inflection. So I'm going to have a point of inflection right here and right here, because we've changed concavity. Now I'm going to have to plug those in to the original. So we're concave up on -infinity to 2/3 minus root 13 over 3 union this chunk over here, 2/3 plus root 13 over 3, comma, positive infinity, concave down in between them. And then we have points of inflection. So let's circle that. Point of inflection. I'm not going to make you watch me type these in here. I'm just going to put at x equals 2/3 plus or minus root 13 over 3. Now, of x at those numbers. In the real world, we'd want to plug those in. Even if we got decimal approximations, plug this into your calculator, each one of those numbers, get a decimal, plug it in there. I mean, raising something like that to the 4th power is going to be a nightmare. I don't think it's instructive to watch me do that. Okay, here we're given the graph of f of x. I want to sketch f prime of x. I'm going to do it over here beside it. And we're not even given numbers. So I don't know, maybe we'll call that a and b right there. Okay, so any place where the graph is decreasing, my derivative is going to be negative. Any place where I have a local min, a local max, the derivative is going to be 0. So the derivative is going to be 0 at these 3 locations. Let's go ahead and put those on. There's A, here's 0, here's B. This is F prime. The derivative is negative in this region and in this region because the graph is decreasing. See, look, we're going downhill, so negative, but getting less and less negative until we hit 0 right there, and then we're positive in this region. So negative, positive until 0. So my derivative is going to have to do something like that. See, it's positive in here, but it's getting smaller and smaller. My tangent lines are getting less and less steep. Look at that tangent line versus that tangent line. See how they're getting less steep? That's because the derivative is getting less positive. Negative in this whole region, but I've got to hit 0 back by the time I get over here. So it's got to do something like that. See, all those derivatives are negative. Graph was decreasing, derivative is negative, and now graph is increasing, derivative is positive. So here, let me break this up into regions. So decreasing, negative derivative, increasing positive, decreasing negative, increasing function, positive derivative. Negative, positive, negative, positive. And of course, it's continuous and nice and smooth. If your function is smooth, your derivative is going to be nice and smooth. Okay, same kind of game over here. First, let's find all of our zeros of our derivative. All of the local maxes and mins right there at about -1. So it's a little before that. The derivative will be 0. Here at, looks like a little before 1. The derivative will be 0. Again at 2. The derivative will be 0. And again, that looks like it's a little more than 3. The derivative will be 0. Okay, and again, let's break this into regions and figure out positive and negative. Increasing function will be a positive derivative. Decreasing function will be negative. Increasing, see, I'm going up from left to right, positive. Graph is decreasing here, so negative derivative, and then increasing, so positive in this region. Okay, so I'm going to be positive, hit 0, go negative in between here and here. So something like that. So positive, negative in this region, hit 0 again right there. Positive in between here, but I have to go back to 0, so I'm going to have to curve back around. You can kind of see what's going on here. Negative in this region between like the 2 and the 3, and then positive again. Now, this is not a hard, fast rule, but this happens often, as long as you don't have any saddle points. Notice how many turning points I had here. I had 1, 2, 3, 4. Look at my derivative. I've got 1, 2, 3 turning points. Notice up here, I had 1, 2, 3 turning points. My derivative only has 2. If your graph is a polynomial, then taking the derivative reduces the degree by 1. The derivative of x to the 5th is x to the 4th, right? 5x to the 4th. So your derivative will usually have 1 less turning points than the original. Not always, but usually. To add 1, 2, 3, 4 turning points, the derivative is 1 less than that, only 3. Okay, here we're going to graph this guy. So he's 2 pages long. All right, first let's find our intercepts. To find x-intercepts, we always set the function equal to 0, always, in every situation. So x to the 4th minus 4x cubed equals 0. I can pull an x cubed out and get x minus 4. So I get 0 and 4. Intercepts are points, not numbers, so that'll be 0, 0, and 4, 0. What about the y-intercepts? Actually, I already found it. To find the y-intercept, you always plug in 0 for x. That's just 0. So my y-intercept is the point 0, 0. I already had it right there. Okay, let's find our critical values, figure out where we're increasing and decreasing. That's what the derivative gives us. So taking the derivative, 12x squared. All right, now let's take the second derivative. Let me make that guy a little smaller first, though. All right, so my second derivative. What do we get? 12x squared minus 24x. I would pull a 12x out of that. And we get what? X minus 2. So I have two possible points of inflection. X equals 0 and x equals 2. There and there. So now we do a sign chart for the second derivative, 0 and 2. And I'm going to use this factored form, and I'm going to do this by writing my factors on the side. 12x, x minus 2. So I'm going to make my little table here. I'm going to figure out the sign of each of these factors in each region. Okay, this guy switches at 0. He's negative before 0 and positive after. This guy switches at 2. Right there, he's going to be negative before 2, positive after. So both of these are negative, and that's a positive. It's a negative right there. And now just multiply, because those are multiplied. 2 negatives makes a positive, 1 negative makes a negative, and 2 positives makes a positive. You could also absolutely just pick a test point in each region and plug into the second derivative and check the sign. This is just quicker. All right, so we are concave up in these two regions and down in this region. So these are both points of inflection. If you switch concavity, you've got yourself a point of inflection, as long as that point is in your domain, as long as that x value is in your domain. So we're concave up on two different regions, negative infinity to 0, that's this region, and then 2 to infinity. And then we're concave down, 0 to 2. All right, and now we got to plug 0 and 2 to find our points of inflection. Not in here. I know I'm going to get 0 there. Not in the derivative, but in the original. 0, that's easy. That's just 0. Plugging in 2, I'm going to get 16. Here, I'll do it in the calculator for you instead of doing it in my head. So 2 to the 4th. Minus 4 times 2 to the 8th third, which is 8, negative 16. So plugging in a 0, I get 0. I already knew that. That's my x and y intercept. And 2, negative 16. 0, 0, 2, negative 16. All right. So at 0, we do not have a local max or a min because the graph stays decreasing and then increasing after here. Okay, this is right now. Decreasing from negative infinity up to 3, this entire region, 4x squared is always positive. Increasing from 3 to infinity. I'm going downhill here, uphill here, so I've got a local min at 3, comma, and if you plug that in, you get negative 27. I already checked that. Okay, and there's my local extrema. This guy here is going to be a saddle point. This is where we're going to change concavity, but not have a local max or min. Okay, so this was at 2 there. At 3, we're down at negative 27. Okay, so we were decreasing all the way to 3. And then increasing from 3 afterwards. So we know the graph's got to go down to here and then increase. So like rough sketch, something like this. I'm going to fix this. This is not perfect yet. Something like that. That's just my decreasing and increasing. Now we're going to fix that up by doing our concavity. We know we're concave up until 0. So concave up, remember, kind of looks like a right side up bowl. So like this. That's concave up. Concave down from 0 to 2. So that point right there. So concave down. Well, I'm trying to draw like an upside down bowl, but just this half of it. Concave down there, and then concave up again the rest of the time. So all of this chunk will look like a right side up bowl. So my graph is going to look basically like this. So all of this is concave up. This chunk in here is concave down. There's my point of inflection, and there's a point of inflection. See how you can tell we're switching right there from concave up to concave down. Okay, now a couple word problems. Okay, this problem sounds a lot more complicated than it actually is. So we've got some exponential function. You should know from college algebra, an exponential graph looks like that. And my y-intercept here is going to pass through the point 0, 1. Now I'm going to build a rectangle out here at 17, 0 that comes up, touches the graph. One corner is going to be on this guy. Okay, so we're going to come back here to some point and have a rectangle that looks like this. We're not building the rectangle out this direction. We're building it inside here. Now, we don't know where. Like it could be right here, or it could be some little tall, skinny rectangle. We don't know. We want to maximize the area. So let's call this point here X. Then let's find the area of this rectangle. So here's my width. That width right there is 17 minus X. Because this is 17, this is X, so that's 17 minus X. And the height is the function value. That height right there is e to the 12x, whatever that x value is. So area will be e to the 12x times 17 minus x. And now that's what we want to maximize. Now it's actually not a bad problem at all. We have a function of one variable. We know how to maximize functions. Anytime you see the word maximize or optimize, Take the derivative, set it equal to 0. Okay, yeah, we'll go ahead and use product rule here. We could distribute that out, but I don't think we're still going to need product rule. So derivative of the first times leave the second alone plus leave the first alone times the derivative of the second. The derivative of the second is just -1. Okay, and now I think it would be helpful to clean this up. So we're going to get 12 times 17. Let's see what that is. (204) e to the 12x minus 12 e to the 12x minus one of those, e to the 12x. And then these, I cleaned all that up so I could combine those. I'm missing an x here. That times that, yeah, x there. These two are like terms, that one's not. So we get 203 e to the 12x minus 12x e to the 12x. And I want to know where this equals 0. So I can factor out that common factor there of e to the 12x. And I get 203 minus 12x equals 0. This guy never equals 0. So I just set that equal to 0. And that's all. And we get x equals, I think we get 203 over 12. Okay, then let's find the maximum area. So the question only asks for the value of x. We're done. That's the answer. Like, that's it. That's the whole problem. But just for fun, it's all right here. For fun, let's find the maximum area. That was my answer. So we're just going to plug that back in here. And like here, I'll do it in a calculator. So that was my area function. Now, I think I've shown you this before, but I'm going to show you a shortcut. If you had to plug in a whole bunch of different values here, you can go into y equals, let's clear this out, type in your function. So I want e to the 12x times 17 minus x. Oh, type something on there, x. Okay, and then I could graph it if I wanted to. I don't know why I already had a graph on there. Oh, because this guy's turned on. Turn that guy off. Now I'm looking over here. I want in between 0 and 17. Otherwise, this rectangle doesn't make any sense. I could set my window from 0 to 17. I'm just showing you what the graph would look like. We don't actually have to look at the graph. My y values are gigantic. So I'm going to need to make my y values. I know they can't be negative. Maybe we'll go up to 1,000 just to get a picture here. Still not big enough. So my y values are gigantic. Like just for, I've already come this far. Let's go a little further. Oh, those y values, let me make sure I plug that in right. I mean, we're going to get something like when I plug in that number right there, that's bigger than 10. We're going to get something like e to the 120th power. We're getting some gigantic number. So someplace up here is the maximum. I don't know if it's worth looking anymore. The point I was trying to show you is you can go here to calculate. Second, calculate, hit value, And now I can just plug in that and it will spit out the Y value that goes with that. And that's 1.2. Notice right there, see that little E or that capital E? That's 1.2 times 10 to the 87th power. Yes, I was not making my graph nearly big enough. 1.2 times 10 to the 87th. Again, the question didn't ask for it. We were done right there. All right, what we got here? Now, this is an interesting one. We got two cars moving towards an intersection. One car is 50 meters north of the intersection and moving down. Let's call him car A, and his velocity, his dy dt, is negative 12 meters per second because he's moving down. The other guy's west, and that'd be over here, moving away from the intersection. So he's moving this way. See, this is X. His X is decreasing at negative 25 meters per second. Okay, we want to check distance though. So like we want to be careful with this sign here. Even though his X value is decreasing, if we just call X his distance from, so I'm not thinking of X as a positive or negative number. If I think of X as his distance from the origin, his distance is getting bigger from the origin. His distance is getting smaller from the origin. Okay, I want to find the distance between these guys. Let's call this, maybe we'll call it R. So if this is X and this is Y, so Y is this guy's distance from the intersection, X is this guy's distance from the intersection. I want R as a function of time because I want to plug in 4 seconds, dr dt. Okay, how do X, Y, and R relate? X squared plus Y squared equals R squared. There's a relationship between my variables. This is a related rates problem. You're always going to draw a picture and find a relationship between your variables. Then take the derivative of everything with respect to time. It's almost always with respect to time. Take derivative with respect to time of both sides of everything. All right, so taking the derivative with respect to time, I'm going to get 2x dx dt plus 2y dy dt equals 2r dr dt. Everybody here is a function of time. So when I take the derivative with respect to time, I pick up it's implicit differentiation. I pick up a dx dt, dy dt, dr dt. I can divide out these twos and get x dx dt plus y dy dt equals r dr dt. Okay, this is who I'm after. I want that, but when do I want it? I want it at a particular moment in time. I want it after 4 seconds. So I'm going to have to figure out x and y at 4 seconds. So this guy started, so I'm going to have to do a little bit of math here to figure this out. So I need x at 4 seconds and y at 4 seconds. And I'm going to need r at 4 seconds. So I started here at 50 meters north, y at 0 was 50. That's a 5. And it's decreasing by 12 meters per second. So y at 4 will be 50 minus 4 times 12, because it's going down by 12 meters per second. So I think that's going to be 2, because that's 50 minus 48. X of 0 was what? 20. So X at 4 will be 20 plus, because my X is getting bigger. X is my distance here. My Y's were getting smaller. That's why we had the negative. My X's are getting bigger at 25 meters per second. And it's 4 seconds, so that's 120. How am I going to find R at that time? Well, I know at any point in time, X squared plus Y squared equals R squared. So R of 4 squared will be X at 4 squared plus Y at 4 squared. So R squared equals 120 squared plus 2 squared. And we'll get our fancy calculator out here. 120 squared. 2 squared is 4. And then we want to take the square root of that. It's 120.17. Wait, what did I just say? 0.17. And that's meters. That's the distance between the cars at that particular moment. All right, now I can plug everything in and solve for R. Oh, dr dt, right there. That's what I'm after at 4 seconds. All right, so plugging in my X, 120, dx dt was 25. Plus Y was 2. dy dt was negative 12. Equals R, 120.017 times dr dt. Okay, so I'm going to add those together and then divide by that. I'm going to do that all in the calculator here. So that's 120 times 25. I can just do that in my head, minus 24. Yeah, minus 24. Get that answer and then divide it by that answer up there, 120.01, and I'll type a few decimals, 666 there. 24.8 meters per second. Remember, that's measured in meters per second. We're looking for a rate of change, a speed. And I don't remember what I just said. 24.8. Okay. There are a lot of different versions of this problem. Like this is a really good related rates problem. You're always going to have this relationship. You're always going to have this after you take the derivative. The key is to getting the right signs on your dx and your dy. Are your distances getting bigger or smaller? If they're getting smaller, it's a negative. If it's bigger, it's a positive. And then you're always going to have to either see, sometimes they'll give you a time like they did here. Other times they'll say, how quickly is the distance changing when X equals 7? They'll give you an X or a Y value, and you have to find the other two guys at that spot at that time. Okay, now a bunch of L'Hopital's problems, and then we're done. Okay, so to find these limits, first we got to check which type we have of indeterminate form. So try plugging it in. If somebody asks you to take a limit, the very first thing you do is try plugging it in. So if I plug in 0, I get sine of 0, that's 0. Sine of 0 is 0. This goes like 0 over 0. That's my indeterminate form. Then I can use L'Hopital's. So that limit will equal, using L'Hopital's, remember that's how we write it, limit as x approaches 0. Take the derivative of the top and the bottom. It is not quotient rule. I'm not taking the derivative of the fraction. I'm taking the derivative of top and bottom. And you should just be able to do both of those derivatives in your head. Now you try plugging it in again. Cosine of 0 is 1. So that's 1. That's 1. We get 3/5. If you get a number, you're done. That's your answer. Okay, what about here? Natural log of x, his graph, looks like this. If I try to approach 0 from above, that guy goes like infinity. He goes to negative infinity, but that's a version of infinity. Same with 1 over x. His graph looks like this. As I'm approaching 0 from above, he goes to infinity. My indeterminate form here is infinity over infinity. That's a candidate for L'Hopital's rule. So that limit will equal, using L'Hopital. Now, sometimes on these, it's better to flip everybody over. Sometimes it's not. Let's just try taking the derivative, top and bottom, and see if things get better. And they will. The derivative of natural log of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. Check both of those on your own. Now, you might look here. I've seen this happen. I've seen this every time I teach this class, this happens. People will get here and they'll just try plugging in it immediately and go, oh, look, I'm still getting infinity over infinity. And they'll keep trying to apply L'Hopital's, and they'll keep making this uglier and uglier. Once you get here, see if you can clean up. If you've got logs in the problem, I guarantee you this is going to happen. Once you get here, you're going to be able to clean up. So do a little keep, change, flip. This is limit as x approaches 0 from above, 1 over x times negative x squared over 1. That's just limit as x approaches 0 from above of negative x, because so I get some cancellation there. That's just 0. I'm done. Okay, here I want the limit as x goes to infinity. So now I'm looking at end behavior of this fraction. And remember, dominating behavior. That's the way I want you to think. Like, I want you to be able to look at this and just know what the answer is. We're going to justify it using L'Hopital's. Any exponential will beat out any polynomial, which will beat out any logarithm. So this is a polynomial on top and an exponential on the bottom. The exponential is going to win. Both the top and bottom are going to infinity. The top is going to infinity much faster. So that limit's going to be 0. If the bottom wins, the answer is 0. If the top wins, it's some kind of infinity. If they cancel out, if you've got the same behavior, top and bottom, then you might end up with some like ratio of leading coefficients or something. So the bottom's going to win. We're going to get 0. Let's check that. Our type here is infinity over infinity. So we apply L'Hopital's rule. So that limit equals limit as x goes to infinity. Take the derivative of the top, 6x. Derivative of the bottom, 10 e to the 2x. That's still infinity over infinity. Top and bottom still both go to infinity. But notice my degree went down. So the top is now prettier looking than it used to be. So we're going to try L'Hopital again. Limit as x goes to infinity. Derivative of the top is just 6. Derivative of the bottom, 20e to the 2x. Now, the top does not go to infinity anymore. The top, this is just a number over infinity. That limit is always 0. Okay, this should have read on this one, limit as x goes to infinity of 1 plus 2 over x raised to the 5x. I'll fix that in the document. Okay, anytime you've got junk raised to a power, let's check our indeterminate form. The inside here, 2 over infinity goes to 0. We get something that looks like 1 raised to the infinity. So this goes like 1 to the infinity. That's one of our indeterminate forms. That indeterminate form, let's call this inside L. And we want to take the log of both sides. So natural log of L will equal natural log of this stuff. Now that 5x will come down on ground level. Oh, and I forgot my log. So 5x times log of 1 plus 2 over x. All right. And now we're taking the limit of both sides. So take the limit as x goes to infinity. Limit x goes to infinity. Okay, so we get something here that looks like infinity times, well, this thing goes to 0. We get natural log of 1. Natural log of 1 is 0. We get something of the form infinity times 0. Anytime you get infinity times 0, you want to rewrite this as a fraction. We can only use L'Hopitals on fractions. So I'm going to have this over here will equal the limit as x approaches infinity. And I want to write this as a fraction. And my suggestion to you is anytime you have a log, leave the log on top. And then rewrite this guy, that 5x is 1 over 5x in the bottom. Now let's check our form. 2 over x goes to 0 as x goes to infinity. 1 plus 0 is 1. Natural log of 1 is 0. 1 over infinity goes to 0. This is of the form 0 over 0. Now L'Hopital's applies because I've got a fraction of indeterminate form 0 over 0. Now I can use a L'Hopital. So I'm going to have limit as x goes to infinity. And keep in mind this whole time that what we're finding is the natural log of the limit of L. So at the end, I'm still going to have to get rid of this natural log, but that'll come later. All right, derivative of natural log of anything is 1 over that thing times the derivative of what's inside. The derivative inside here will be negative 2 over x squared. And on the bottom, the derivative of 1 over 5x. Remember, we're not using quotient rules. Derivative of the top over derivative of the bottom. That's negative 1 over 5x squared. Let's do a little keep, change, flip. So I haven't done any calculus here. This is just algebra. I'm going to have 1 over 1 plus 2 over x times negative 2 over x squared times 5x squared over -1. Those x squareds cancel, those negatives cancel. I get 10 over 1 plus 2 over x. And I'm taking the limit as x goes to infinity. This right here goes to 0. I get 1 plus 0. The limit here in the bottom is just 1. This entire limit is just 10. That's not my answer, though. So what I have is natural log of L equals 10. So make both sides powers of E. L equals E to the 10th power. On these ones that look like this, have this form, you're always going to get E to something. Okay, now what if we had the original problem as it was written? So just for fun, that I'll come back and do this guy in a minute. What if we had limit as x approaches 0 of, what was it, 1 plus 2 over x to the 5x. So we still get to this spot right here. So we would have natural log of L, and that's in a limit, x goes to 0. I just want to show you how we would have done the original problem. So like everything would have been the same up to here. We would just have a 0 right there. That's the only thing that's changing. This is weird looking now. This is not an indeterminate form. I cannot use L'Hopital's again. The top is a constant, and the bottom, when x goes to 0, the bottom goes to infinity. So I would have to clean this up a little bit. So maybe multiply top and bottom by x. So that would be limit as x goes to 0 of 10x over x plus 2. Now when I take the limit as x goes to 0, the top goes to 0, the bottom goes to 2, that limit's just 0. But that was not my limit I'm after. That's natural log of the limit I'm after. So ln of L equals 0. Make both sides powers of E. That limit would have been E to the 0, which is 1. Okay, so that was the original problem. And if you wait until after I've like already fixed the document here, you won't even see that. You'll just see infinity on yours. Which is that's the problem I would put on your test. Okay, finally, this guy here. Remember the very first thing you try when you're taking a limit is try plugging it in and see what happens. Otherwise, you're going to get the wrong answer. If I just plug in 0, I'm going to get 4 over -2. I get -2. I'm done. That's the limit. There's no calculus. Well, I mean, calculus is the study of limits. So technically there's calculus, but there's no L'Hopital. If I tried L'Hopital, I'm going to put here, this is wrong. If I tried L'Hopital, I would get limit as x goes to 0 of 6x over 1. I would get 0. But that is wrong. First thing you try when you're plugging in a limit or evaluating a limit is try plugging it in. If you get a number, you're done. If you get 0 over 0 or infinity over infinity, you use L'Hopital's. If you get 0 over a number, that's the same thing as this. 0 over non-zero is 0. That's what happened here. Say we get 0 over 2. That's 0. All right. That's a good place to stop.